Hello and welcome to Lecture 56 of my class from Data to Decisions. I'm Chris Mack, your instructor, and this is our second lecture on the topic of robust estimation, and in particular, this lecture is on robust regression. What is robust regression? Well, in ordinary least squares regression, we minimize the chi-square. We find the smallest sum of the squares of the residuals. But it's not robust. It's not robust because even one bad data point, one outlier or point from the tail of the distribution can be enough to throw off the regression. We see that residuals are squared before summed up, and so an outlier or a point that's way off in the tail of a distribution is weighted very heavily. It's weighted as the square of its deviation from the model. The breakdown point is 1 over n. We've discussed various remedial measures. If we find an outlier, especially an influential outlier, or if we discover that we have non-normal distributions of our residuals, there are things we can do about that. They tend to work okay when we only have a couple of data points or only slightly non-normal distributions. But if we have a lot of contamination, and that can really mess up even our ability to detect outliers. Also, it's not always easy to automate these kinds of regressions. Tends to be very manual. We look carefully at trying to understand what each interesting data point is telling us. Sometimes, though, we need regression approaches that we can automate without having a lot of manual intervention, or we want regression approaches that can handle a fairly large amount of contamination so that we don't have to rely on procedures that assume only a little bit of contamination, one or a few outliers, in order to detect them. In other words, we need something called robust regression. One approach to robust regression is called least absolute deviations. Instead of minimizing the sum of the squares of the errors, minimize the sum of the absolute values of the deviations or residuals. So we take our data point, subtract off the model, take the absolute value, sum those up, and we will try to minimize that. In other words, outliers will be weighted linearly, not quadratically. So they'll be much less influential. One of the problems, though, is that the absolute value is a function with a discontinuity at the origin. Because of that, we can't take derivatives, and we can't set derivatives equal to 0 as a way of minimizing our function. We can't use our normal approach, our matrix approach towards minimizing S. We have to use other techniques in linear programming. Sometimes these techniques don't provide a unique solution, and sometimes they result in some what we call local minima instead of a global minima. So it looks like we're minimizing S, but in fact there's other solutions that have even smaller values of S. We just don't find them. This is one of the difficulties with this kind of approach. If you can't take the derivative of your function, set it equal to 0 in order to find the minimum. It's interesting to note that the least absolute deviations is the maximum likelihood estimator for the case of a double exponential distribution, so a distribution that falls exponentially on both plus and minus away from the mean, away from 0 for our residuals. Again, it suffers the same problem of not having a derivative at 0. But if that happens to be a good model for our distribution of residuals, the double exponential, well, then this might be, in fact, the best approach to use. It is less efficient, like all of our robust estimators is. The standard error, the coefficients are about 26% bigger than OLS. Sometimes we describe efficiency as 1 over 1.26. So So it'll be about 80% efficient. Another name for this is the minimum L1 norm regression. Probably the most popular type of robust regression is M-estimation. M stands for maximum likelihood like estimation. There's also a S estimation and an L estimation that people have used, but by far M estimation has become the most popular way in which we do robust regression today. This is kind of a generalization of the way ordinary least squares works. Take some general function of the residuals, and then we try to minimize the sum of this function of residuals. For ordinary least squares regression, the function is simply squaring the residual, right? So there could be other functions besides a square that we can use. But we want certain properties for this function. Some of those properties, for example, the absolute value signs don't possess. We always want our function to be non-negative. We want our function of 0 to be 0. That is, if our residual is 0, we don't want that to contribute to our sum. We want it to be symmetric, so a plus and a minus residual should be the same. And we want it to be monotonic, so if the residual is bigger, then we want this function to be bigger. So we want to penalize large residuals more than we penalize small residuals. Right? Those are all kind of generic properties that make a lot of sense. But the last one allows us to be more effective in finding a minimum of this sum S. That is, we want a continuous derivative with respect to the coefficients. That enables numerical stability and our ability to find minima. Then we're going to implement M-estimation using something called iteratively reweighted least squares, which I'll discuss in a moment. All right. Recall how ordinary least squares works. We have S equal to the sum of the residual squared. Then we're going to take the derivative with respect to every parameter in our model and set it equal to 0. Find the value of the parameter that minimizes S. In our case, we take the derivative of epsilon with respect to our parameter. We're going to get 2 times the residual multiplied by the derivative of the residual. And since it's a linear regression, the derivative with respect to that coefficient is simply going to give us the value of that predictor variable. So I take the residual multiplied by the value of the predictor variable, sum over all the data points, set that equal to 0, and solve. I do that for every single parameter, and I solve the simultaneous equations. Right? That's how we do ordinary least squares. Now, for our M-estimator, we're taking a generic function h of the residual. So I'm going to have to take the derivative of h with respect to the residual multiplied by the derivative of the residual with respect to the parameter. So that gives us this formulation. So depending upon the function h, I have to plug in that derivative of h with respect to the residual. After that, I do everything the same. So let's do something interesting. Let's define a weight as being 1 over the residual times the derivative of this function h with respect to the residual. Well, given this formulation, I can solve for this derivative, dh d residual, as simply being the residual times the weight. Right? So now my d-squares minimization is equivalent to dh d residual times the kth value of the parameter. Set that equal to 0 after summing, but dh d residual is residual times this weight, and so it looks like this. Just a little bit of an algebra exercise. Except once I recognize this, I can see what to do. This is nothing more than weighted linear regression. If I take weight times the residual times the value, set it equal to 0, do that for every one of my parameters, solve all of those simultaneous equations, this is exactly how we do weighted linear regression. Now we have a scheme that we can use to do M estimation. It goes like this. Guess the weights. Yep, guess them all to be 1 to start with. Do a linear regression, get a fit, that gives you a bunch of residuals. Once you know the residuals, then I can calculate this weights using this formula. Once I know the weights, I plug them in and do a weighted linear regression. That gives me a new set of residuals, which I can then calculate a new set of weights, and then I iterate. I iterate until the values converge. So we call this iteratively weighted least squares. It allows me to take advantage of all the capabilities of weighted least squares regression that we already have very easily, solve these equations and solve for the optimal. And that's exactly how this robust M estimation works. The only thing left to do is define some good functions H that we can use. And there are a variety of functions we can use. One of the most common is called the Huber M-estimator. What we're trying to do here is attempting to get the best of both worlds of the least absolute deviation estimator and a least squares estimator. What we'll do is we'll make our function, our penalty function for having residuals, to go as the residual squared, just like our least squares estimator does, but only out to a certain value of residual. Once the residual gets above that, then I'll do an absolute value of the residual. So I'll weight it linearly past a certain value k. The most common value is the one Huber picked when he developed this, k equal to 1.345 times the standard deviation of the values. So if we pick that, it turns out that the Huber M-estimator is 95% as efficient as ordinary least squares. We're only suffering a 5% loss in efficiency. It's very, very manageable. And yet, for extreme deviations, we're weighting as the absolute value of the deviation rather than as the square of it. So we're not nearly as sensitive to extreme residuals such as outliers. Once we get a set of residuals and we want to analyze those residuals, we will generally studentize them, externally studentize residuals, but instead of using the standard deviation to studentize them, we'll use the median absolute deviation as our estimate of scale to studentize them. And that way we have a robust estimate of our studentized residuals as well. All right, let's look at this M-estimator. Least squares function is simply the residual squared. So here's the residual in units of standard deviation. Here's the residual squared. All right, so if I'm 5 standard deviations away, I'm weighting the sum 25 standard deviations when adding them up. The Huber M-estimator, on the other hand, looks like residual squared out to about 1.4 residuals, standard deviations, 1.4 standard deviations away. Then it becomes a straight line. So if I go 5 standard deviations away from the mean, my function is only weighting 6 standard deviations squared instead of 25. So it's weighting these extreme points much lower so they don't influence my regression nearly as much. Another popular M-estimator is called the bisquare estimator. I think it was Tukey who proposed this. And this is even more robust because after you get out to some distance away, in this case, about 4.7 standard deviations away from the mean, so 4.5 standard deviations away from 0 for our residuals, the weighting becomes a constant. So If I'm 20 standard deviations away or 50 or 100 standard deviations away, I don't increase the weighting at all. It levels off. Here's in fact, the equation for that bisquare estimator. And you can see that for large residuals, I add the same value to my sum of errors, S, so that 10 standard deviations away or 100 standard deviations away, I penalize the function for that data point the same amount. Another way of looking at how these estimators work is by looking at the weights. Remember, we're doing essentially a weighted regression here. What the Huber M-estimator does is it weights all the data points to be 1 out to 1.4 or so standard deviations away. And it starts weighting them lower and lower and lower. Excuse me. The bisquare weights, on the other hand, immediately start to drop off, and they go to 0 so I get to about 4.7 standard deviations away. So I'm simply weighting those data points to be 0. I just ignore them. And so I can throw in some really extreme values, and they don't affect my regression very much at all. These estimators can be very robust, in particular the bisquare estimator, right? Because, again, I can throw in a super extreme value, and it doesn't affect my regression hardly at all. This is great, especially if you're doing some automated stuff. You don't want to look through, you have big data, let's say. You don't want to look through every data point and make sure nothing's going wrong. The bisquare estimator can really work well. But it does suffer from finding local minima. In other words, we're trying to minimize the value of S, finding the parameters that produce that minimum, but we might run into a local minima instead. Therefore, another approach is to start with the Huber M-estimator because it gives a unique solution. There's only one solution that it will find in the minimum. And that could be a really good starting point for iterating and trying to find the solution with the bisquare estimator. And so this is very commonly done if we want to use the more robust bisquare estimator. Both M-estimators and the least absolute deviation can tolerate large deviations in Y. But I can still have problems with overly influential outliers. If it has both a large deviation in X and a large deviation in Y, it can still pull my regression away. As an aside, robust estimators make good outlier detectors. Why is that? Well, when you're all done, get the weights that you gave data points. If some of the weights are set to be 0, bisquare estimator, or set to be very low for M-estimator, well, that's an indication that is an outlier. In particular, the bisquare estimator with a weight of 0 means I'm throwing that data point out. So we can use, in fact, these robust estimators as outlier detectors. But, as I said, we still have a problem with the potential for a influential outlier. That is, if it's extremely big in X and extremely big in Y, its very first regression can pull the whole regression towards that point, and then we'll never detect it as an outlier. To help with those admittedly kind of extreme and rare cases, we sometimes use bounded influence regression. Try to make sure that no data point has too much influence. We can use a least trimmed squares, where we do a regression and we delete some percentage of the most extreme residuals, and then we perform OLS on the rest. It has to have a large data sample for that to work. And again, if you don't look at what you're doing, you might throw out very important data. The least median squares is probably the most popular of the bounded influence regression. It minimizes the median of the squares of the residuals rather than the sum of the squares of the residuals. This produces a very robust regression, but also an extremely low efficiency in our regression. In other words, the standard errors of all of our coefficients are going to be large. Right? There's no magic bullet here. There's no one thing that does everything, fixes everything, and produces high efficiency, unbiased estimates, which is why we often continue to use ordinary least squares regression and at least try to do the more manual influence and outlier detection to see if we only have a few. We might switch to robust regression when it looks like we have more than just one or two or a few potential outliers. All right, let's look at robust regression. Admittedly, a very quick review of robust regression. You could have an entire full semester college course just on that topic, and I'm sure people do. Textbooks published just on that topic, and we're trying to cover it in one lecture. Oh well, what have we learned? What is the breakdown point for ordinary least squares regression? Explain the basic operation of M-estimators for linear regression. What are some of the difficulties and complications for using robust regression? And finally, among the various robust regression approaches, how do you choose which option to use? In our next lecture, we'll actually do some robust regression using functions in R. Till then.